Okay, next question we have says a small plane is flying due north, so example 2, at 150 kilometers an hour when it encounters a wind from the east at 80 kilometers an hour. What is the resulting ground velocity of the airplane? Now, the bottom part, though it doesn't do too much for our calculations, is important, okay? The resultant ground velocity. And that should be the part I'm highlighting. I'm not sure why I highlight the other stuff. The ground velocity of the airplane, okay? What's happening is we have to be relative to where we're standing. So we're assuming that the plane is heading due north 100 kilometers an hour from someone standing still on the ground. Same with the wind traveling 80 kilometers an hour. That's very fast, actually. 80 kilometers an hour east if you're standing on the ground. If I was running in that same direction, we could use vectors to even explain this idea. Let's say that the wind was heading, let's do wind in blue. The wind was heading 80 kilometers an hour this way, but with my amazing speed. So here's 80 kilometers an hour. Let's say I was also traveling, though, the same direction. I decided to go for a run, and I was traveling at maybe 5 kilometers an hour in the same direction. What would the relative or speed of the wind be in reference to me running in that direction? So these are parallel vectors. Let's say I'm running the exact same direction as the wind. It wouldn't be 85 because we wouldn't be adding them. Think of how much faster is the wind going.
75.
Yes, 75, okay? So had I been moving, the actual speed of the wind would actually only be 75 kilometers an hour in reference to myself. Just like people standing on an airplane. If you're standing on a plane, okay, and maybe somebody's running on the plane at 5 kilometers an hour, they're going 5 kilometers an hour faster than you on the plane, okay? But if someone's standing on the ground and a person is on a plane running 5 kilometers an hour, they're going the speed of the plane plus the speed they're running at. So they're actually moving faster than the plane is in relative to you standing on the ground. So that bottom or that last sentence is just important in terms of how we're going to calculate this. Most of our questions will be done with ground velocity, so don't worry about having to reference too much, but I want to make sure you guys understood that point. Okay, so we can get rid of this. I run much faster than that, by the way, in case you're wondering. Okay, so I drew the wind this way. I did want to ask you guys first about it, but if this is due north and the wind is coming from the east, what direction is the wind actually traveling? It's actually traveling west, okay, because the wind is coming from the east. All right. The other thing is the plane is headed directly due north. Now these aren't perfectly to scale. We're going to put our numbers in here. The plane is traveling at 150 kilometers an hour. Okay. So what's happening is we'll call this vector P for the plane and vector W for the wind. What do we need to do in order to find out the resultant vector of P when W hits it? Anyone know? What operation? Yeah. Yeah, we'll use Pythagorean theorem, but why am I using Pythagorean theorem? What type of vector operation am I using? Anyone know? What's that? Yeah, we're adding them. And that's exactly right. We are going to use Pythagorean because it's going to create this. But what I want you guys to realize, so we're going to be adding these together. So let's think of it, remember when I said that we're telling a story, we're following the lines? So we're going to be actually adding vector P plus vector W, okay? And that's going to create a new resultant vector, or essentially P plus W, whatever that is. So I want you guys to think, okay, we're going to travel through vector P first, okay? So that means we go up vector P, and then we're at this point. Well, from there, the wind is going to push us 80 kilometers an hour in a westerly direction. So in other words, this vector moves to over here, okay? And then we follow vector W from there. So this is the point we end up at now. I'll move some of that other stuff over for us. Going west at 80 kilometers an hour, and that was our point. So we're exactly right. To find the resultant vector, we'll do that in green, let's say. The The resultant vector is going to be here. This is essentially P plus W. And because we're heading due north and the other one's coming directly from the east, we're creating a right angle triangle. Okay, so because we have a right angle triangle, we can use Pythagorean's theorem to solve this. Okay, what would I do in order to solve for P plus W? What is Pythagorean's theorem? Anyone remember? Yeah, that's right. And our c squared is our hypotenuse, or in this case, our resultant vector. So c squared plus a squared plus b squared. The other two are as important. We're going to replace a with vector p. So vector p squared plus vector w squared is going to be equal to, I can name this vector, or I can leave it as pw, p plus w. So I can write it this way as absolute value of p plus w squared, okay, which can get a little confusing. Or I can actually give it its own resultant vector. Maybe we call it the new direction of the plane, so I'll call it vector n, okay? So I'm going to replace pw with n just so it's a little easier for me to understand. So vector n squared is going to be equal to vector p squared plus vector w squared. Now the directions of these vectors are important. They're not as important for finding the magnitude of it. The magnitude of it is going to be the magnitude of it, but the direction in the end will be very important. Okay? So our n squared is equal to 150. Did I say that's p? Yeah. 150 squared plus 80 squared. 170. Oh, final answer is 170. Do you guys know how to carry this all out? You're okay with it? Okay, so vector n is equal to 170 kilometers an hour, okay, in the end. So we know that the plane now travels at 170 kilometers an hour, so it's actually going faster than it was before, which is pretty good. But what direction is it heading, which is very important? Do we know what these angles are?
45.
Are they 45?
Yeah.
We're 100% sure?
No, they're not.
Anyone know why they wouldn't be 45?
Because they're not equal.
Yes, this side, 150, is not equal to 80. So these are not angles that are going to be the same in the triangle. They're going to be different. So we're going to need to find out, how do I find out angles of a triangle? Anyone know any formulas? We can use sine law. This is a right angle triangle. There's even an easier one we can use. What's that? 30, 60, 90 is a special triangle. We don't know if this fulfills that. Someone said it over here. SOHCAHTOA, the really easy one. These are primary trig ratios. This is a right angle triangle, so we can use our SOHCAHTOA rules, okay? In fact, we have all three sides of this, and when using all three sides of this, we could even use cosine law, but again, that's more in depth. Let's just use our SOHCAHTOA. I want to know this angle here, because his old direction was this one here. I'm going to find out his new direction clockwise, okay? When we talk about a bearing is moving clockwise from where we were before. So what that means is clockwise from here, this will be the angle. But in order to find that angle, I'm going to find the angle inside the triangle and then subtract from 360. So because I have all the sides, I can really do whatever I like. I'm going to use the sides we had before. I'm going to use tangent, and we're going to call this theta. Tan theta is equal to the opposite. Well, opposite of that angle is 80. And the adjacent to that angle is 150. Okay, so we get tan theta is equal to, bring up our calculator here, 80 divide 50. Oops, sorry, 150. 0.523. Okay, and then to solve this, we do second function tan. 28, yeah, roughly 28 degrees. Okay. So theta is equal to 28 degrees. So this angle in here is 28 degrees. But if I want to find the bearing from north, I actually have to take 360, which is a full circle, and subtract our 28 degrees, which will give me what? 332 degrees. So if I was to describe this as a bearing, we'd say this is at a bearing, or the plane is headed 170 kilometers an hour at a bearing of 132 degrees. And we know a bearing is moving clockwise from due north.